Hi everyone, my name is Shikhar Vashit, and today I'm going to talk about my work on MASR, which stands for Multi-Label Aware Speech Representation Learning. This is a joint work with Anjali Raj, Shikhar Bharadwaj, Shriram Ganapati, and Min from Google Research. Let us first understand what is the main motivation behind this work. So, as we all know that self-supervised learning has been a great success in NLP and vision domain. It has led to drastic improvement on several downstream tasks ranging from machine translation to image captioning. Inspired by their success in speech, also these techniques have been explored. Here I have listed some subset of relevant works which utilize self-supervised learning in speech. However, the focus of all these works have been to capture semantics to improve performance on ASR. The main hypothesis of our paper is that encoding both semantic and non-semantic information will give us more optimal and universal speech representation. For concreteness, let me define what do I mean by semantic and non-semantic information in speech. As shown on the left, semantic signal refers to capturing content of a speech utterance, which a model learns through mass language modeling based laws. The non-semantic information refers to global properties of a speech signal, such as its speaker information, in which language it is spoken, what was the prominent emotion of the utterance, etc. This information, unlike semantics, is spread throughout the signal. Let us briefly take a look at the already existing work in this domain. The most related method to our work is laser, which was proposed by our own group and was published at InterSpeech. In laser, given any speech encoding method such as wave to vec, bird, best arc, etc., we obtain frame level representation for each speech sequence in a batch, as denoted here by Z1, Z2, and so on. These are used to compute MLM or contrastive loss as done in the original encoding method. Apart from this, we introduce a pooling function which gives an aggregated representation of the speech signal. This is used for computing the hard triplet loss as shown here. The goal of the hard triplet loss is to push apart the representation of utterances which belong to different languages and make representation of utterances belonging to the same language close to one another. This makes the encoder to implicitly embed language metadata in the speech representation, thus improving performance on tasks which can benefit from this information, such as language identification. In this section, we'll talk about our proposed framework measure. So, existing speech identification systems make mistakes while distinguishing similar languages. As shown in this example, for existing systems, it is hard to distinguish between Hindi and Marathi, which are more related language, than distinguishing between Marathi and English, which are quite distinct from one another. In Maser, we introduce multiple changes to the laser framework. The first change is the introduction of projection layer, which is a metadata specific transformation applied on the aggregated speech representation. This allows Maser to incorporate multiple metadata information together. For each type of metadata, a different projection layer is applied to optimize for them simultaneously. Apart from that, we also include a metadata encoder, which instead of using metadata directly, first embeds it in an embedding space. For instance, in the case of language metadata, we embed each language using its wave to wave representation, which embeds different language properties. This metadata encoder is specific to each metadata. Using the metadata embeddings, a pairwise distance matrix is computed across the utterances in a batch. This matrix is used to decide the positive and negative instances for the hard triplet loss. For language metadata, this ensures that languages which are similar to one another are likely to become negative samples, making the model better at distinguishing them. In this section, we'll talk about our experimental results. We utilize datasets such as Vox Populi, Common Voice, Babel, etc. for pre-training measure. Overall, this involves training over 429,000 hours of data, which spans across 75 languages. We evaluate the obtained models on language identification tasks on Flores and Dhoni datasets. We also evaluate performance on ASR on multilingual Libri speech. Finally, we use wave to wave BERT, best RQ, and laser as our baseline methods for comparison. On language identification tasks compared to best RQ, we get 12.2 relative improvement on Flores dataset, whereas this increase is 2.6 on Dhwani, which contains more real world audio data from YouTube. The results also demonstrate that Maser is more effective than its predecessor Laser on both these datasets. This shows language-wise improvement on Flores dataset. Here, the star indicates that language which does not overlap with the pre-training data, and the regular ones indicates the language which do not overlap. The results are for the languages with 25% absolute change in performance. Overall, we find that the performance improves for most of the languages, dr- and this holds even for the non-overlapping languages, which shows the generalizability of our proposed method. This result shows that how Maser is helpful to reduce confusion among similar languages. So here we are looking at three Serbo-Croatian languages for which the original model was not performing well. However, after Maser pre-training, the model becomes much more effective at, at distinguishing them. In this slide, we show that how the choice of metadata encoder influence the downstream language identification performance. As a result, demonstrate as we vary the metadata encoder, the language identification performance also changes drastically. Thus, the quality of metadata encoder matters for the Maser model. Finally, we report the performance on ASR task. The result shows that Maser pre-training does not degrade the performance on ASR. As we can see, word error rate on multilingual debris speech remains almost the same across all the methods. Finally, I want to conclude with its future scope. So the idea of utilizing metadata information present in datasets used for pre-training has not been explored much in NLP and vision. The extending Maser to other modalities will be an interesting direction to explore. Maser allows to utilize multiple metadata information simultaneously. However, it is not clear how much weightage should be given to each metadata. In the current method, all of these hyperparameters need to be adjusted manually. Thus, automating them can be an interesting direction. Finally, our focus has been on language identification. However, more analysis can be done on slightly unrelated tasks such as emotion recognition, etc. And this can be very interesting. So I want to conclude uh, with this slide. Like overall, we propose a Maser framework uh, which allows to incorporate multiple metadata information in any self-supervised pre-training method. We demonstrate through our results that Maser is effective for a language identification task and does not lead to any degradation on ASR performance. Finally, the method gives state-of-the-art performance on Flores and Dhwani datasets for language identification. Thank you everyone for listening.